All right, welcome to this explainer. Today, we're diving into something super fascinating. We're going to bridge a century of incredible foundational history with some of the absolute most cutting-edge civil engineering modeling available today. We're looking at the Krishnarajasagara Dam, or the KRS Dam for short, which is this monumental structure that literally transformed an entire region. And then, well, we're going to look at the exact science of what would happen if the whole thing came crashing down.
So I want you to start by asking yourself this. What happens when a century-old architectural marvel is pushed way beyond its limits? Imagine a structure that was designed to be this immortal provider of life, suddenly facing unthinkable forces of nature. What happens to the folks living downstream? How fast does that water actually move? Well, today we don't just have to guess. We have the data and we have the software to simulate the unimaginable.
Section 1. Architects of Modern Mysore, Visionaries of the Past. You know, before we can virtually destroy this dam, we really need to understand how it was built in the first place and the immense vision behind it. Let's travel back to the minds behind what became known as Model Mysore.
Back in 1895, Nalwadi Krishnaraja Wadiyar was crowned Maharaja, and he took direct control shortly after in 1902. He was just absolutely dedicated to the comprehensive development of the Mysore state. Under his reign, and alongside the brilliant Sir M. Visvesvaraya, who became Dewan in 1912, the region saw growth like never before. I mean, think about this. By 1900, they had already kicked off the Shivana Samudra hydroelectric project. That was the very first of its kind in all of Asia. And they didn't stop there. They established everything from the Mysore Bank in 1913 to a local university and fully modern agricultural systems.
And honestly, Jawaharlal Nehru really hit the nail on the head when describing the chief architect of the dam, Sir M. Visvesvaraya. At Visvesvaraya's centenary celebration, Nehru noted that while a lot of people, talk a big game but fail to deliver, Visvesvaraya was the exact opposite. You spoke less, worked more. He was a guy who built practical marvels that changed millions of lives, plain and simple.
Moving on to Section 2, Building the KRS Dam, the crown jewel. All that incredible work ethic and visionary planning ultimately culminated in their most ambitious project. Let's take a look at their absolute crowning achievement. Built in 1924, right across the Kaveri River, the KRS is a gravity dam. But what makes it a true, bona fide marvel of its era is that it was built primarily with stone masonry and cirque mortar. No modern concrete here. This wasn't just a big wall of stone. It became the absolute lifeblood for the region. It catered to the drinking water and irrigation needs of Mysore, Mandya, and eventually even Bangalore. And the sheer scale of the thing? 1,400 million cubic meters. That is the gross storage capacity holding back a massive artificial reservoir. It captures a catchment area of nearly 11,000 square kilometers. To put that into perspective, that is an astronomical amount of water sitting behind those stones.
So how do you wrangle all that water? Well, the complexity of the structure is staggering. There are 152 installed gates needed to control the design flood discharge. They're situated at different levels, they have varying capacities. It's basically a finely tuned, massive machine of water management.
Section 3, the unthinkable scenario, a modern analysis. Because we have to ask what happens when the water becomes too much for those 152 gates. This is where we pivot from triumphant history to a really high-stakes scientific disaster model.
First, we need to quickly clarify a technical term: overtopping failure. It's exactly what it sounds like: a catastrophic event where water levels rise so incredibly high, usually from extreme unprecedented rainfall, that the water actually flows right over the top of the dam. The intense pressure and erosion from this flow eventually cause the structure to breach or break apart entirely.
So to understand the specific risks to the KRS Dam, we're looking at a 2020 research paper published in the International Research Journal of Engineering and Technology. A team of civil engineers basically said, okay, let's simulate the absolute worst-case scenario for the KRS Dam. They wanted to see exactly what would happen downstream if the dam suffered one of these overtopping failures.
Section 4. Simulating a catastrophe, the science of disaster. How do you even begin to test the destruction of a century-old dam without actually breaking it? Let's get into how modern engineers predict a catastrophic flood.
Enter a tool called KRS. This is a highly sophisticated 2D hydraulic modeling software developed by the Hydrologic Engineering Center of the U.S. Army Corps of Engineers. It is literally the gold standard for predicting flood behavior and analyzing the downstream effects of a theoretical dam breach.
Let's break down the exact workflow these researchers used. It's a three-step process. First up, input geometric data. This means feeding the software high-resolution satellite topography of the land, the specific gate details, and the exact dimensions of the dam. Second, they run an unsteady flow simulation, computing how the water will behave over time. And finally, the software generates highly detailed visual maps of the hazard.
Okay, this is where it gets genuinely terrifying. Based on empirical formulas for masonry dams, the engineers calculated that if the dam fails from overtopping, a 729-meter wide gap would form. And look at that formation time, 0.25 hours. That's 15 minutes. If this dam breaches, it breaks apart almost instantaneously, releasing an absolute wall of water.
Section 5. Mapping the flood impact, tracing the fallout. What does that wall of water actually look like as it moves? Let's look at the visual results from the HEC-RAS simulation to really understand the geographical impact.
First up is the velocity map. If you look at the warmer colors right by the breach point, they indicate incredibly violent speeds. The simulation predicts maximum velocities reaching nearly 65 meters per second right at the point of failure. That's not just a flood. That is a destructive force that would literally scour the landscape.
Next, we have the depth data. This illustrates the staggering maximum water depths that would just completely submerge the areas downstream. The dark blue zones closest to the dam show water depths reaching up to 40 meters. Guys, that's equivalent to a 12-story building completely swallowed by rushing floodwaters. No way around it. That's massive.
And honestly, this one is probably the most critical map of all, the flood arrival time map. Put yourself in the shoes of someone living downstream looking at this. The colors tell you exactly how much time an area has before the water hits. Green means you have a bit of time, red means the water is practically there the second the dam breaks. This is exactly the data emergency managers need to figure out who to evacuate first and how many minutes they have to pull it off.
So what are the real-world stakes here? Well, a breach would affect over 50 villages just on the stretch down to T. Narasapura. And the researchers pointed out that the flood wave would likely keep going, potentially causing submergence all the way down to the Metter Dam in neighboring Tamil Nadu. This is absolutely not just an academic exercise. Simulating this destruction is how we create emergency action plans, or EAPs. By mapping out the absolute worst-case scenario, authorities can build early warning systems and evacuation routes that save thousands of lives.
Which brings us to our final provocative thought. How can the disaster simulations of today actually protect the architectural legacies of yesterday? By understanding exactly how and why a structure might fail, we can better reinforce it, we can monitor its weak points, and we can make sure that the brilliant legacy of visionaries like Wadiyar and Viswesvaraya stands strong for another 100 years. Thank you so much for joining me on this explainer. I really hope you found this intersection of history and modern engineering as fascinating as I did. Keep learning, and I'll catch you on the next one.